Hello, this video is going to talk a little bit more about the editor from the previous video. One aspect we didn't touch on was the Axial probe placement, which is the fourth tab here. Now, I said that the editor wasn't a licensed product, but the design two tabs are, so if you've got the relevant license, these will be enabled. And I'll just flick through the tabs from yesterday, and we've got an Axial probe positioning tab. What this allows you to do is it allows you to place the probes actually across the blade's edge so that you can make sure the probe sees the biggest displacement it can for each particular mode shape. Now, if you've got the mode shape information, and if you look at our website and if you look at the manual for the editor, there's file formats are in there. And if it's in the correct format, you can load that mode information into this editor. Now, I'll load the modes, and I'll load the tip deflection. And as you can see, we've got 3 modes on display. Now, these modes are from a steel blade from a military Viper engine that we have got for another project. So these are real. First 3. We don't refer to the front or the back of the blade. There's no leading or trailing edge measurements. It just depends on the order your data's in. So all measurements will be with respect to the first value in your data tables. So if you start at the back of the blade and work forward, then this is the back of the blade. If you start at the front of the blade and work back, then this is the front of the blade. So we don't care in the editor. It's up to you to work out with respect to what edge the data's been taken. So, table on the left, got 3 modes, color coded as always. We've got the peak value of the mode shape in millimeters. So the blue mode clearly is bigger, you can see that at 0.7 of a millimeter. We have a priority, which gives the calculator some idea of how to treat each individual mode. Each individual mode. We have a sensitivity, which is a percentage of the maximum value, the peak value. So if I move the slider across to the peak on the blue mode shape, you can see that we're at 100% of that mode. Okay, so we're also at 100% of the green mode, and we're at 61% of the orange mode, or yellow. If you press the calculate button, it did move. It finds the position of the most deflection for all the modes summed together. So that not necessarily the biggest mode peak, but it weights them. So the percentage sensitivities. So if you add those 3 up, you get 261.31, which is this number down here. So this is the total sensitivity number. This should be, as you move the slider across, the largest number you see. And it's picked that and said, at this point, if you put the probes here actually on the blade, you'll get the biggest set of sensitivities. Now that may exclude one mode at the expense of another, but you can see that on the graph. If you had a lot more mode shapes, then you might have to do it by hand. But what this number will give you is the sensitivities for each mode as you move the slider across. I've got another file which I can load, which will demonstrate that, which is, I've altered this file slightly. It's the same file, but I've added a 4th mode, which is fictitious, which is this one here. And you might think if you press the button, it would pick this position here, because it looks like it's got the biggest total sensitivity. If you press the calculate button, it chooses that one, and it comes up with a score of 305.6%. As if you move the cursor over to the peak of this one, it's 301%. So that should give some idea about how it decides the best position and the best place actually for the probes. What I also want to talk about is the fifth column, which is uncertainty, this one here. Now, we use probes with a numerical aperture of 0.22. Okay, that's the default value. If you know that, and you know the clearance, you can work out the uncertainty of your measurement at that position on the blade. And you can demonstrate this by looking at the uncertainty of the mode I've just added, which is this one here, which is currently at 0.6%. Now that's because these red lines are the red lines are the plus and minus uncertainty figures, depending on, this is based on 2 millimeters clearance. So because the top of this is relatively flat, you get a smaller change from the boundaries of the two red lines, which is the uncertainty. But if you was to put your probes here, for instance, in real life, and that mode was real, or mode shape, sorry, was real, then you'd have a horrendous uncertainty, 35%. That may or may not be very unattractive depending on what you're trying to do. So this tool gives you an idea and allows you to make certain trade-offs. It's unusual to find a perfect sweet spot, and you may well find, as I said yesterday, that there are places where one mode is only responsive at one end of the blade and another mode that's responsive at the other end. In that case, you need 2 rows of probes because you can't be sensitive to both. There's no compromise position. So we think with this tool really does enable you to think quite carefully about your placement of your probes across the blade, and it also allows you to take into account the clearance depending on the numerical aperture of the fibre you're using. Okay, I'll leave it at that. Thank you.